I shall present an introduction to robotics. But before I begin, let me give you a brief introduction about myself. Okay, I did postdoctorate in robotics from South Korea, and I am PhD in mechanical engineering with specialization in robotics. I did my master's and bachelor's in mechatronics engineering from UT Lahore. I am interested in wearable robots for paraplegia and hemiplegia patients. What are these things? You can go and Google it. And I'm also interested to implement my robotic skills for cerebral palsy patients. Again, if you are more interested about this, things like cerebral palsy, hemiplegia, paraplegia, please go and Google it. I'm also looking uh, I'm also looking to conduct research on socially intelligent and interactive robotics. I have also interest in work. I have also interest working in dynamic motion planning for multi-robot system. So these are my details and my interests. I'm also uploading these lectures on my YouTube channel. You can go over there and watch recording of this whole lecture. These are the contents of my today's lecture. I'm following this book, which I'm showing you here. I will take you from the start, and this book will take you from the start and will give you a glimpse of advanced robotics as well. So I really like this book. I hope everyone enjoy reading this book, and I wish that many of you be inspired. Um, before I go on, but before formally begin this studying this book, let me give you something amazing which is achieved and still in progress in robotics. How can you, here you can see a man with different equipment installed in his body. You can notice his bionic eye, and here her ear, her heart, and you can see his bionic eye, his bionic ear, you can see his bionic heart, bionic liver, hip and knee joint, and then you can also notice his amputated right leg. So guess what? Robotics is working to replicate these human organs lost in some sort of accidents or simply because of growing old. Imagine a world without crippling, a place where nobody grows old ever. Um, Many of the elderly people lose their charm of life because of such weaknesses. So they just want to sit back in their homes and they just want to pass their life, which is which is really non-productive. These people are extremely experienced and very valuable for the society. If we could use their abilities, imagine how revolutionary would it be. So if the person has lost her hearing property, his hearing, uh, that can be that can be um, installed using bionics and robotics. Again, if someone is having problem in his heart, this can be it can be replaced with robotic heart, and similar is case with the liver, knee, hip joint, and palms. These are really amazing things which are being achieved in robotics. Let me show you a picture of the girl. This lady has lost her arm. She wants to move just like any other person. She wants to live like a healthy person. But how roboticists can achieve it? We have gone to the moon, but we haven't looked into ourselves yet. Still exploring. In this picture, you can see countless wires and sensors. These wires pick signals from her brain, and these are the same signals she was generating before her limb was cut off. These signals are still there. Her brain is still generating signals to move her limb. But the only problem is that there is no limb. So if we can put a device here which can understand this signal and again make a movement similar to what she thinks, then we can recover our loss. And that's what we are going to do. That's what roboticists are doing in rehabilitation. Um, if we can do it, this would be really good. But let me show you an MIT professor's motivational video about that. So in this video, you would see, the title of this video is "Let Us Run," and I think it's self-explanatory, and you will enjoy this.
Looking deeply inside nature through the magnifying glass of science, designers extract principles, processes, and materials that are forming the very basis of design methodology. From synthetic constructs that resemble biological materials to computational methods that emulate neural processes, nature is driving design. Design is also driving nature. In realms of genetics, regenerative medicine, and synthetic biology, designers are growing novel technologies not foreseen or anticipated by nature. Bionics explores the interplay between biology and design. As you can see, my legs are bionic. Today, I will tell human stories of bionic integration, how electromechanics attached to the body and implanted inside the body are beginning to bridge the gap between disability and ability, between human limitation and human potential. Bionics has defined my physicality. In 1982, both of my legs were amputated due to tissue damage from frostbite incurred during a mountain climbing accident. At that time, I didn't view my body as broken. I reasoned that a human being can never be broken. Technology is broken. Technology is inadequate. This simple but powerful idea was a call to arms to advance technology for the elimination of my own disability and ultimately to the disability of others. I began by developing specialized limbs that allowed me to return to the vertical world of rock and ice climbing. I quickly realized that the artificial part of my body is malleable, able to take on any form, any function, a blank slate for which to create perhaps structures that could extend beyond biological capability. I made my height adjustable. I could be as short as 5 feet or as tall as I'd like. So when I was feeling badly about myself, insecure, I would jack my height up. But when I was feeling confident and suave, I would knock my height down a notch just to give the competition a chance. Narrow wedge feet allow me to climb steep rock fissures where the human foot cannot penetrate, and spiked feet enable me to climb vertical ice walls without ever experiencing muscle leg fatigue. Through technological innovation, I returned to my sport stronger and better. Technology had eliminated my disability and allowed me a new climbing prowess. As a young man, I imagined a future world where technology so advanced could rid the world of disability, a world in which neural implants would allow the visually impaired to see, a world in which the paralyzed could walk via body exoskeletons. Sadly, because of deficiencies in technology, disability is rampant in the world. This gentleman is missing 3 limbs. As a testimony to current technology, he is out of the wheelchair, but we need to do a better job in bionics to allow one day full rehabilitation for a person with this level of injury. At the MIT Media Lab, we've established the Center for Extreme Bionics. The mission of the center is to put forth fundamental science and technological capability that will allow the biomechatronic and regenerative repair of humans across a broad range of brain and body disabilities. Today, I'm going to tell you how my legs function, how they work, as a kind of case in point for this center. Now, I made sure to shave my legs last night because I knew I'd be showing them off. Bionics entails the engineering of extreme interfaces. There's 3 extreme interfaces in my bionic limbs: mechanical, how my limbs are attached to my biological body; dynamic, how they move like flesh and bone; and electrical, how they communicate with my nervous system. I'll begin with mechanical interface. In the area of design, we still do not understand how to attach devices to the body mechanically. It's extraordinary to me that in this day and age, one of the most mature, oldest technologies in the human timeline, the shoe, still gives us blisters. How can this be? We have no idea how to attach things to our bodies. This is the beautifully lyrical design work of Professor Neri Oxman at the MIT Media Lab, showing spatially varying exoskeletal impedances, shown here by color variation in this 3D printed model. Imagine a future where clothing is stiff and soft where you need it, when you need it, for optimal support and flexibility without ever causing discomfort. My bionic limbs are attached to my biological body via synthetic skins with stiffness variations that mirror my underlying tissue biomechanics. To achieve that mirroring, we first developed a mathematical model of my biological limb. To that end, we use imaging tools such as MRI to look inside my body to figure out the geometries and locations of various tissues. We also took robotic tools. Here's a 14-actuator circle that goes around the biological limb. The actuators come in, find the surface of the limb, measure its unloaded shape, and then they push on the tissues to measure tissue compliances at each anatomical point. We combine these imaging and robotic data to build a mathematical description of my biological limb, shown on the left. You see a bunch of points or nodes. At each node, there's a color that represents tissue compliance. We then do a mathematical transformation to the design of the synthetic skin, shown on the right. And we've discovered optimality is where the body is stiff, the synthetic skin should be soft. Where the body is soft, the synthetic skin is stiff. And this mirroring occurs across all tissue compliances. With this framework, we produce bionic limbs that are the most comfortable limbs I've ever worn. Clearly, in the future, our clothing, our shoes, our braces, our prostheses will no longer be designed and manufactured using artisan strategies, but rather data-driven quantitative frameworks. In that future, our shoes will no longer give us blisters. We're also embedding sensing and smart materials into the synthetic skins. This is a material developed by SRI International, California. Under electrostatic effect, it changes stiffness. So under 0 voltage, the material is compliant. It's like floppy like paper. Then the button's pushed, a voltage is applied, and it becomes stiff as a board. We embed this material into the synthetic skin that attaches my bionic limb to my biological body. When I walk here, it's no voltage. My interface is soft and compliant. The button's pushed, voltage is applied, and it stiffens, offering me a greater maneuverability of the bionic limb. We're also building exoskeletons. This exoskeleton becomes stiff and soft in just the right areas of the running cycle to protect the biological joints from high impacts and degradation. In the future, we'll all be wearing exoskeletons in such common activities such as running. Next, dynamic interface. How do my bionic limbs move like flesh and bone? At my MIT lab, we've studied how humans with normal physiologies stand, walk, and run. What are the muscles doing, and how are they controlled by the spinal cord? This basic science motivates what we build. We're building bionic ankles, knees, and hips. We're building body parts from the ground up. The bionic limbs that I'm wearing are called biomes. They've been fitted to nearly 1,000 patients, 400 of which have been U.S. wounded soldiers. How does it work? At heel strike, under computer control, the system controls stiffness to attenuate the shock of the limb hitting the ground. Then at mid-stance, the bionic limb outputs high torques and powers to lift the person into the walking stride, comparable to how muscles work in the calf region. This bionic propulsion is very important clinically to patients. So on the left, you see the bionic device worn by a lady. On the right, a passive device worn by the same lady that fails to emulate normal muscle function, enabling her to do something everyone should be able to do, go up and down their steps at home. Bionics also allows for extraordinary athletic feats. Here's a gentleman running up a rocky pathway. This is Steve Martin, not the comedian, who lost his legs in a bomb blast in Afghanistan. We're also building exoskeletal structures using these same principles that wrap around a biological limb. This gentleman does not have any leg condition, any disability. He has a normal physiology. So these exoskeletons are applying muscle-like torques and powers so that his own muscles need not apply those torques and powers. This is the first exoskeleton in history that actually augments human walking. It significantly reduces metabolic cost. It's so profound in its augmentation that when a normal, healthy person wears the device for 40 minutes and then takes it off, their own biological legs feel ridiculously heavy and awkward. We're beginning the age in which machines attached to our bodies will make us stronger and faster and more efficient. Moving on to electrical interface, how do my bionic limbs communicate with my nervous system? Across my residual limb are electrodes that measure the electrical pulse of my muscles. That's communicated to the bionic limb. So when I think about moving my phantom limb, the robot tracks those movement desires. This diagram shows fundamentally how the bionic limb is controlled. So we model the missing biological limb, and we've discovered what reflexes occurred, how the reflexes of the spinal cord are controlling the muscles. And that capability is embedded in the chips of the bionic limb. What we've done then is we modulate the sensitivity of the reflex, the modeled spinal reflex, with the neural signal. So when I relax my muscles in my residual limb, I get very little torque and power. But the more I fire my muscles, the more torque I get, and I can even run. And that was the first demonstration of a running gait under neural command. Feels great. We want to go a step further. We want to actually close the loop between the human and the bionic external limb. We're doing experiments where we're growing nerves, transected nerves, through channels or microchannel arrays. On the other side of the channel, the nerve then attaches to cells, skin cells and muscle cells. In the channels of motor channels, we can sense how the person wishes to move. That can be sent out wirelessly to the bionic limb. And then sensors on the bionic limb can be converted to stimulations in adjacent channels, sensory channels. So when this is fully developed and for human use, persons like myself will not only have synthetic limbs that move like flesh and bone, but actually feel like flesh and bone. This video shows Lisa Millette shortly after being fitted with 2 bionic limbs. Indeed, Bionics is making a profound difference in people's lives.
Oh my God, I can't believe it! It's just like I've got a real leg. Now don't start running.
Now turn around and do the same thing walking up. Walk up, get on your heel to toe like you would normally just walk on level ground. Try to walk right up the hill.
Oh my God.
And pushing you up?
Yes, I'm not even, I can't even describe it.
It's pushing you right up.
Next week, I'm visiting the centers. Thank you. Thank you. Thank you. Next week, I'm visiting the Center for Medicare and Medicaid Services, and I'm going to try to convince CMS to grant appropriate code language and pricing so this technology can be made available to the patients that need it. Thank you. It's not well appreciated, but over half of the world's population suffers from some form of cognitive, emotional, sensory, or motor condition. And because of poor technology, too often conditions result in disability and a poorer quality of life. Basic levels of physiological function should be a part of our human rights. Every person should have the right to live life without disability if they so choose. The right to live life without severe depression. The right to see a loved one in the case of seeing impaired. Or the right to walk or to dance in the case of limb paralysis or limb amputation. As a society, we can achieve these human rights if we accept the proposition that humans are not disabled. A person can never be broken. Our built environment, our technologies are broken and disabled. We, the people, need not accept our limitations, but can transcend disability through technological innovation. Indeed, through fundamental advances in bionics in this century, we will set the technological foundation for an enhanced human experience, and we will end disability. I'd like to finish up with one more story, a beautiful story, the story of Adrienne Haslett Davis. Adrienne lost her left leg in the Boston terrorist attack. I met Adrienne when this photo was taken at Spaulding Rehabilitation Hospital. Adrienne is a dancer, a ballroom dancer. Adrienne breathes and lives dance. It is her expression. It is her art form. Naturally, when she lost her limb in the Boston terrorist attack, she wanted to return to the dance floor. After meeting her and driving home in my car, I thought, I'm an MIT professor. I have resources. Let's build her a bionic limb to enable her to go back to her life of dance. Brought in MIT scientists with expertise in prosthetics, robotics, machine learning, and biomechanics. And over a 200-day research period, we studied dance. We brought in dancers with biological limbs, and we studied how do they move? What forces do they apply on the dance floor? And we took those data and we put forth fundamental principles of dance, reflexive dance capability, and we embedded that intelligence into the bionic limb. Bionics is not only about making people stronger and faster. Our expression, our humanity can be embedded into electromechanics. It was 3.5 seconds between the bomb blasts and the Boston terrorist attack. In 3.5 seconds, the criminals and cowards took Adrienne off the dance floor. In 200 days, we put her back. We will not be intimidated, brought down, diminished, conquered, or stopped by acts of violence. Ladies and gentlemen, please allow me to introduce Adrienne Haslett Davis, her first performance since the attack. She's dancing with Christian Leitner.
Ring my bell, ring my bells. 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 Sometimes you love it, sometimes you don't. Sometimes you need it, then you don't, and you let go. Sometimes we rush it, sometimes we fall. It doesn't matter, baby, we can take it real slow.
Ladies and gentlemen, members of the research team, Elliot Rouse and Nathan Kartzi. Elliot and Nathan. Woo. So this was a motivational video about biorobotics. That's what we want to achieve. This is simply amazing. I cannot say enough more than that. We can bring back these broken people back into life. We can give them hope. We can make a world a beautiful place. So let's formally start robotics. So what is robotics? Let me define that. Robotics is concerned with the study of those machines that can replace human beings in the execution of tasks, as regards both physical activity and decision making. So whatever we want to do, we want something which can replace and human being and decision making and physical activity. So this is called robotics, and this covers a lot of things. But let me give you the basic principles. It's based on three fundamental laws. First of all, a robot may not injure a human being or through inaction or on a human being to come to the harm. So the first thing is it must not injure a human being. Second principle is that a robot must obey the orders given by human beings, except when such orders would conflict with the first law. This is the second basic principle, and these principles are really important. And third principle is that a robot must protect its own existence as long as such protection does not conflict with the first or second law. These are the three basic fundamental principles for the robotics, and all robots are built based on these laws. Some of the idiots are trying to develop robotic military robots, which is not good. This is a road which, if started, there is no end to it. This is even more dangerous than building a nuclear bomb. But nobody talks about this because superpowers are busy. Okay, so the essential component of a robot is a mechanical system endowed in general with the locomotion apparatus such as wheels, crawlers, mechanical legs, etc., and manipulation apparatus such as mechanical arms, end effectors, artificial hands, etc. As an example, the mechanical system in this figure is shown consists of two mechanical arms. So here are two mechanical arms, each of which is carried by a mobile vehicle. I believe that you cannot see it, but assume there is a mobile vehicle, which is a locomotion apparatus, and this is a robot mounted on that. The realization of such system refers to context of design of articulated mechanical system and choice of materials. The capability to exert an action, both locomotion and manipulation. Locomotion means going from one place to another, and manipulation is to manipulate something, is provided by an actuation system which animates the mechanical components of the robot. So actuators are there to make a move. The concept of such system refers to context of motion control, dealing with servo motors, drives, and transmissions. So what are actuators? If we say straightforwardly, these are motors together with drives and transmission system. The capability for perception is entrusted to a sensory system which can acquire data on the internal status of the mechanical system. Sensors such as position transducers, etc., as well as on the external status of the environment, such as exteroceptive sensors, force sensors, cameras, etc. The realization of such system refers to context of material properties, signal conditioning, data processing, and information retrieval. So what do we do? Sensors collect data from the environment, from the robotic system, and then send it to a control system. The capability for connecting action to perception in an intelligent fashion is provided by a control system. which can command the execution of action in respect to the goals set by a task planning technique, as well as the constraints imposed by the robot and the environment. The realization of such system follows the same feedback principle devoted to the control of body function, possibly exploiting the description of the robotic systems components, which is modeling. The context is that of cybernetics, dealing with control and supervision of robot motions, artificial intelligence, an expert system, the computational architecture, and programming environment. So in simple, sensors collect data. Um, Based that data is analyzed and sent to control system. Control system generates command, analyze it, and generate appropriate command, sends it to actuator, sends it to the actuators, and actuators make the robot move. The mechanical structure of a robot manipulator consists of sequence of rigid bodies. So there are many rigid bodies, one, two, three, interconnected by means of articulated joints, articulations, which are joints. And manipulation is characterized by an arm that ensures mobility, a wrist that confers dexterity, and an end effector that performs the task required for the robot, requires of the robot. So all these kinds of things are manipulators. But another part of the robotic mechanical structure is a mobile robot. The main feature of a mobile robot is the presence of mobile base, which allows the robot to move freely in the environment. Unlike manipulators, such robots are mostly used in service applications where extensive autonomous motion capabilities are required. Let's have some brief introduction of both of these robots. So here you can see Cartesian manipulator and its workspace. This is a one type of robot. It has particular only movement in this direction, and this direction. And this is gonna be its workspace. So it can move from one point, from this point to this point, from this to this point, and again from this point to this point. This is the whole play. This is the square. This is the box type of thing in which this robot can only move. Then we have gantry manipulator. Again, these kind of robots are used in PCB manufacturing or machining process. Again, this can only move in this direction, and this direction. Then we have cylindrical manipulation. You can see it has two joints. One of the joint can have to and fro motion, and the other another joint can have to and fro motion, but the base can rotate. So based on that, it generates kind of cylindrical shape. Then we have spherical manipulator and its workspace. Again, based on the structure, it generates its workspace, basically spherical. This one can move, this one can rotate, this joint can rotate, joint can move in to and fro motion, and this can move also in to and fro motion. So the overall it makes spherical. Then we have SCARA manipulator and its workspace. Again, this joint can rotate, this joint can rotate, and this joint can move up and down. So that would be the workspace. I'm showing you these different kind of robots because when you look at them, you can see, okay, this is the workspace they can move in, and that's going to be their kinematics. Then we have anthropomorphic manipulator and its workspace. These are type of robots, manipulators, which are just like our human arm. Our human arm is just like anthropomorphic manipulator. We shall discuss about these robots later. But before that, let's look into some other robots. Then we have manipulators with parallelogram. So this robot has some special link along with this link. This can move its motion, and it can also limit its motion. So this is manipulator with parallelogram. This is parallel manipulator. So it means these manipulators can These manipulators have multiple actuators, multiple joints. This is really advanced type of robotics. And then we have a hybrid parallel serial manipulator. Okay, now about mobile robots. Basically, we have two types of mobile robots. One is legged mobile robots, in which locomotion is based on legs, and we have wheeled mobile robots, in which there are wheels for the movement. Again, the aerial robots are kind of mobile robots, basically wheeled mobile robots. The only difference is that these robots fly instead of simply um, simply rolling on the floor. The basic dynamic model of these robots are similar. Um, Let me give you three different types of wheels, and these types of wheel will generate different kinds of dynamic modeling in the robots. So one is fixed, so it cannot move, it can only rotate in this direction, and other is steerable, so it can rotate in this direction and also rotate. One is caster, so in the caster wheel has two axes, but vertical axis does not pass through the center, and from which it is displaced by a constant offset. Such an arrangement causes the wheel to swivel automatically, rapidly aligning with the direction of motion of the chassis. So this is really a good feature in that. Now I'm going to give you a basic different types of mobile robots. In a differential drive vehicle, there are two fixed wheels with common axis. So two fixed wheels with common axis, and one or more caster wheels. So this one is going to be caster wheel, typically smaller, whose function is to keep the robot statically balanced. The two fixed wheels are separately controlled in different values of angular velocity may be arbitrarily imposed. Well, this, for example, if motion on of this wheel is counterclockwise, this can be counterclockwise. So this is a differential robot. While the caster wheel is passive, such a robot can rotate on the spot without moving midpoint between the wheels. So this robot can move on the spot, provided that angular velocities of two wheels are equal and opposite. Again, I have told you. Again, a vehicle with the similar mobility is obtained using synchro drive kinematic arrangement, shown in figure 1.14. This robot has three aligned steerable wheels, which are synchronously driven by only two motors through a mechanical coupling, that is chain or transmission belt. The first motor controls the rotation of the wheels. So these three wheels um, control there are two motors. One is to control the speed and direction of these vehicle, and the second motor one motor is to control the speed of this vehicle, and the other motor is to control the direction. So these three wheels move synchronously. As I said, the first motor controls the rotation of the wheels around the horizontal axis, thus providing the driving force through contraction. The second motor controls the rotation of the wheels around the vertical axis, hence affecting their orientation. Note that the heading of the chassis does not change during the motion. So during the motion, heading is not changed. If you want to change the direction, first the vehicle is stopped, and then its direction is changed. Then we have tricycle vehicle. There are two fixed wheels mounted on a rear axle and a steerable wheel in the front. The fixed wheels are driven by a single motor which controls their traction, and two wheels, the steerable number two, while the steerable wheel is driven by another motor which changes its orientation. So we change the direction choosing another motor, mm, acting then as a steering device. Alternately, alternatively, the two rear wheels may be passive and the front wheel may provide traction as well as steering. So this is also possible. The difference between this one is that you can change the direction while the robot is moving. And here you cannot change that direction. Then we have a car-like vehicle, which has two fixed wheels mounted on a rear axle and two steerable wheels mounted on the front axle. As in the previous case, as in the previous case, one motor provides front or rear traction, and the other changes the orientation of the front wheels with respect to the vehicle. So with respect to the vehicles, it changes its orientation. It is worth pointing out that to avoid slippage, the two front wheels must have a different orientation. So if the robot is turning in this direction, for example in this direction, then orientation of these two steerable wheels are different when the vehicle because when the vehicle moves along a curve in particular, the internal wheel, this one, is slightly more steered with respect to the external one. This is guaranteed by the use of specific device called Ackermann steering. So these are the features of car-like mobile robot. Then we have finally which has three caster wheels. So there are three caster wheels usually arranged in a symmetric pattern. The traction velocities of the three wheels are independently driven. Unlike the previous case in a vehicle is omnidirectional. Unlike the previous cases, this vehicle is omnidirectional. In fact, it can move instantaneously in any Cartesian direction as well as reorient itself on the spot. Okay, you may not understand it at this point, but let me give you a brief idea that this robot can move on not only, for example, if this one is moving in this direction, this can also move in this direction as well. This is quite possible without changing the wheel direction because it has specifically designed vehicles, specifically designed wheels for that. Then we have Macron or Swedish wheel. This is a grown-up version of um, um, omnidirectional mobile robot wheels, which are called let me see that. Yeah, omnidirectional or the caster wheels. What are the applications? There are many applications. And the industrial robot, basically, let me define the industrial robot is a machine with significant characteristics of versatility and flexibility. According to the widely accepted definition of the Robot Institute of America, a robot is reprogrammable multifunctional manipulator designed to move materials, parts, tools, or specialized devices through variable programmed motions for the performance of a variety of tasks. Some of the applications are there. Typical applications include palleting, I mean placing objects on a pallet in an ordered way, warehouse loading and unloading, mill and machine tool trending, part sorting, packaging, arc and spot welding, painting and coating, gluing and sealing, laser and water jet cutting, milling and drilling, casting, and many more. You can go about that. Okay, now about the advanced robotics. The expression advanced robotics usually refers to the science studying robots, which marked characteristics of autonomy operating uh, in, in structured or unstructured environments whose geometrical or physical characteristics would not be known a priori. So robot does not know what are the and what is the environment, how to handle it, but it understands and then acts according to its understanding. So here is the Asimo robot. It is picking up a device or something which holds liquid, and it does not know where it is placed. It focuses, it reaches to that bottle, opens it up and pours and then picks up a glass and pours the juice or something into it. So this is really a delicate job. So this is in the domain of advanced robotics. Here is an interesting graph. So these are the areas of advanced robotics in which people are working. So first of all, underwater. Okay. And so there's going to be new installations. Underwater robots, new installations are again there. And then we have defense and rescue and robots, which are again rising, and their development is getting more and more traction. Then we have robots for hostile fields such as battlefields and places where there's places of disasters, such as which has recently occurred in Florida, which we call Irma storm. Then we have medical robots. We have, and then there are many other different kinds of robots. So these are the advanced robotics fields in which people are working, and many robots are being developed. Then we have field robots. The context is that of deploying robots in areas where human beings could not survive or be exposed to unsustainable risks. Such robots should carry out exploration tasks and report useful data on the environment to a remote operator using suitable onboard sensors. Typical scenarios are the exploration of volcanoes, the interventions in areas contaminated by poisonous gases or radiation, or exploration of deep ocean or space. So here is a space robot, is a firefighting robot. So these are typical applications. Then we have service robots. Autonomous vehicles are also employed for civil applications, that is for mass transit system, um, thus contributing to the reduction of polluting levels. Such vehicles are part of the so-called intelligent transportation system devoted to traffic management in urban areas. Another feasible application where the adoption of mobile robots offers potential advantages is museum guided tours. So these are service robots. Technology is ready to perform into commercial products. The prototypes of robotic aids to enhance elderly and impaired people's autonomy in everyday life. Autonomous wheelchairs, mobility aid lifters, feeding aids, and rehabilitation robots allowing paraplegics to perform manual labor tasks are examples of such service robots. So these are all service robots. In perspective, other than an all-purpose robot waiters, assistants, healthcare system integrating robotic and telemetric modules will be developed for the home service management. For home service management systems. These are typical examples of service robots. Then we have surgical robots. So I have a video to share with you, but I think it's worth watching it.
The 4 valves in your heart keep your blood flowing forward. Located between your left atrium and left ventricle, your mitral valve controls the blood flow between these 2 chambers and stops blood from flowing back into the left atrium when the left ventricle contracts. The mitral valve is composed of a front portion, known as the anterior leaflet, and a back portion known as the posterior leaflet. A fibrous ring of tissue called the annulus surrounds the mitral valve. This maintains its shape and helps ensure that the leaflets close completely. Tendinous cords anchor the leaflets to small projections in your left ventricle, called papillary muscles. If you have mitral valve disease, your posterior leaflet enlarges and projects or prolapses into the left atrium. This may result from your cords elongating or rupturing. The damaged valve allows blood to leak or regurgitate back into your left atrium. The only way your left ventricle can compensate for this condition is by enlarging and pumping more volume. This causes your mitral orifice to enlarge, preventing your leaflets from closing properly. To treat this condition, your doctor may suggest a type of minimally invasive procedure called robotic mitral valve repair. Your surgeon will begin the procedure by making 5 small incisions on the right side of your chest. A second surgeon will insert a special camera called an endoscope and other tools attached to the robotic arms through the incisions. These robotic instruments allow the surgeon a wider range of motion and more precision than the normal human wrist. In order to perform your operation safely, the surgical team will stop your heart and place you on a heart-lung machine. This machine takes over the functions of these organs during your operation. A tube, called a cannula, will be inserted into your right groin, draining blood from your heart into the heart-lung machine. The machine will oxygenate your blood and pump it back into your body through another cannula inserted through a small incision in your left groin. Seated at the robotic console, your surgeon will operate the robotic arms and the camera with hand controls and foot pedals. This computerized system will translate the exact movements of your surgeon's hands into precise movements of the robotic instruments. Your cardiac surgeon will have a magnified 3-dimensional view inside your body through a high-definition binocular display. Your surgeon will then make an incision in your left atrium to get to the mitral valve. There are different types of repairs depending on the condition of your mitral valve. A posterior leaflet repair is one of the most common types. During the repair process, your cardiac surgeon will most often remove part of the prolapsed portion of your valve and will suture together the remaining tissue. Your cardiac surgeon will also correct the enlargement of the mitral orifice by suturing a firm band or ring to the mitral annulus. Robotic mitral valve repair is the least invasive and the most precise technique available to treat mitral valve disease. The benefits for patient include no splitting of breastbone, less pain because of no retraction of the chest wall, lower risk of infection and bleeding, allows for high-precision complex mitral valve repair, shorter hospital stay, quicker recovery and return to activity, and significantly better cosmetic results. For more information, contact Cardiothoracic Surgery at NYU Langone Medical Center, Cardiac and Vascular Institute, 212-263.
So imagine that before, without using these surgical robots, what surgeons are doing right now, they open up the whole chest and then they go into the heart and operate it. This is very risky and very painful process. Patient, patients who undergoes this process um, needs to be very healthy because he is all he needs to he really needs to be he really needs he has to recover from this kind of a lot of he has to recover from all of these cuts which are going to be done which for all the patient has to recover really needs to be healthy and very strong to recover all these cuts. So this was really bad and really problematic and very painful. Using minimal invasive surgery, robots can go into the heart without causing a lot of cutting tissues and many things. And these robots are very accurate compared to the human hands. Human hands are quite not as accurate as robots. So that's what the people are doing, and people are really interested. In the next section, I discuss about something basics about robots. So how do we begin with? In all robotic applications, completion of generic tasks requires the execution of specific motion prescribed to the robot. The correct execution of such motion is entrusted to the control system, which should provide the robots actuators with the command. The commands consist with desired motions. The first thing about this is modeling. And what's that? It's a kinematic analysis of mechanical structure of a robot, concerns the description of motion with respect to fixed reference, which we call Cartesian frame, by ignoring the forces and moments that cause the motion of the structure. So it is meaningful to distinguish between kinematics and differential kinematics. So with reference to robot manipulator, kinematics describe the physical and describe the analytical relationship between the joint position and the end effector position and the orientation. So from joint to the end effector is called forward kinematics, and inverse kinematics is from the end effector to the joints. Then we have differential kinematics. Differential kinematics describes the analytical relationship between the joint motion and the end effector motion. So it's called the joint velocity and end effector velocity through the manipulator Jacobian. Then we have planning. Here we have two things about it, with the trajectory planning and motion planning. With reference to the task assigned to the manipulator, the issue is whether to specify the motion at the joints or directly at the end effector. In material handling tasks, it is sufficient to assign only the pickup and release locations of an object, which we call point-to-point motion. Whereas in machining tasks, the end effector has to follow a desired trajectory, which is called path motion. The goal of trajectory planning is to generate the timing laws for the relevant variables, which are called joints or end effector, starting from a concise description of the desired motion. So we are going to discuss about this in chapter number 4. On the other hand, the motion planning problem for a mobile robot concerns the generation of trajectories to take the vehicle from a given initial configuration to a desired final configuration. Such a problem is more complex than that of robot manipulators, since trajectories have to be generated in respect of the kinematic constraints imposed by the wheel. So for example, if robot is no car-like robot, it cannot move in this direction instantaneously. If it is moving first, it has to take a turn like this. So in motion planning, this is really complicated task. Again, the control is very simple. It is realization of the motion specified by the motion planner, by the control laws, and require the employment of actuators and sensors. So what we do is we generate the motion planning, we generate the plan, we give it to the controller based on the model, execute it. Simple. And so I would conclude my today's lecture with that. We can do amazing things with robotics. We discussed different types of robots, and we also talked about robots prospectus in our lives. Let me give you some big names in robotics. This is Professor Andrew D. Lewis. He's working on geometric control, and he's basically working on under actuator robots. This is Professor Jesse W. Grizzle. He's from the University of Michigan. He's working on legged robots. Really amazing person. Then we have Professor Vijay Kumar. He is working on many different fields, but basically he's working on mobile robots and robot corporations. With this, I thank you all for listening to my presentation. If you have any comment or suggestion, please comment below. Thank you.